So I have a few announcements for you. So I posted the first homework. Did you guys see? It's due next week. 2 problems. It's gonna take like 40 minutes. It's not that like long homework. The second announcement, I got approached with people with the Nihiri NSF for internships. Have you guys heard about Nihiri, the natural hazard engineering infrastructure? So basically, if you are pursuing job in the structural engineering field, I know most of you is gonna pick at some point to be an environmental engineer, structural engineer or something. So if you want to be a structural engineer with focus on natural hazard impacts on buildings, some of you will be a structural engineer focused on design of buildings, like you design structures, design bridges. Some of you will be, for example, at some point picked to be a forensic engineer to go assess building damage or something. But if you focus at some point in your career, or you would like to know at some point to be a natural hazard focused engineer, like to develop vulnerability function for building, to work for insurance companies, like insurance companies who assess the premium for a building, like you are gonna pay, for example, a flood insurance for your building per year, like $10,000 or something. Who assesses this? Is a structural engineer. They study the hazard, study the vulnerability of the building, study the exposure of the building, and then they tell the risk of this building to get damaged over the years is gonna be this. So, and actually the pay when you work for insurance companies or risk modeler companies is way much better if you work as a regular structural engineer, like you design beams and columns and frames and foundation. So if you want this, I might forward this email to you because the form is out there and there's a deadline. So you might get an internship there if you are interested, like in jobs like this. Is any of you interested? So should I like forward? Okay. So I'm gonna like maybe send the form in an announcement and you can fill it. And this can be good if you are looking for natural hazards future job. Okay, so for integration and mass, I have a sheet, but this sheet has something like related to calculus, how to do differentiation, like most of the rules of differentiation, the integration and all these stuff. So I might upload it on Canvas, but this not allowed in the exam. Maybe when you're doing your homework, if you want to revise your math background, stuff like this. So this might be helpful. I believe it's just like 5 or 6 sheets. So what is going to be allowed in exams and quizzes and everything? This one sheet. Okay. This one sheet has most of the equations that you need in our course. Okay. So they are divided by the chapter based on the Hibbeler textbook. So you check Hibbeler, you'll find chapter 12. Particle motion. So you'll find all the equations that you need. So talking about this, let's see what equations that we have from last time, from chapter 12. So in chapter 12 so far, if you guys remember, we had 3 equations. The one that relates the velocity with the distance, and the velocity is the time rate if you change ds dt. Or we can write it as s dot. And the acceleration is the d velocity dt, or we can write it as a v dot or s double dot. So this is the relationship between the velocity, time, and distance. Acceleration, velocity, time. So the time is there. If the time is not in the problem, we said that we have another equation that says that the acceleration is equal to v dv ds. Or we can write it as a ds equal v dv, same way, right? And from these equations, like for example, if I give you a problem,
Professor VDT, you mean?
which one?
VDT?
This one?
That's the last one. ADS, VDT?
No, this is ds. Okay, so the one that has dt is this relationship, the velocity with time. But for this one, if you remember, we take dt alone, and we said that the tt is equal to ds over v, and dt is equal to dv over a. So ads is equal to dv, so it's this one, right? So this rule doesn't have dt, so that's actually special if Your problem doesn't have time, but has distance, acceleration, and velocity. So you just use this rule right away. So this is the integral, this is the differential relationship between the distance, velocity, and acceleration. But we integrated this. What if I give you the velocity and I want the distance? So you need to integrate the velocity. What if I give you the acceleration and I ask you for the velocity and the distance? So you need to do a first degree integration to the acceleration to get the velocity, and you need to do another integration to get the distance. So here is the SVA, distance, acceleration, distance, velocity, acceleration. So if you want to get, if I give you the distance as a function of time, you need to differentiate it to get the velocity. So you take d dt of dt of ds. And the velocity to get the acceleration, so you need to take d dt of the velocity. But if we want to go back, if you have the acceleration and you want to get the velocity, what I'm going to do? You need to do integration. And if you have the velocity and you want to get s, you need to do an integration. You know what is this? So differentiation from distance to velocity, another differentiation from the velocity to the acceleration. But if you want to go back from the acceleration to the velocity, so you want to do integration with respect to dt, and definitely you'll have t naught and t naught and t, dt. So this is, and from this, if you remember in the last 10 minutes from last lecture, we came across, or we proved two things. For non-constant, or let's say variable acceleration, we proved these two equations, s minus s naught equal to the integration from t naught to t v dt. How did I get this? By doing this integration. Okay? And the second equation was v minus v naught is the integration from t naught to t a dt. So from this equation, if you integrate a, you will get v. So this is v, and this is the integration of a with respect to the time. And I have v minus v naught because this is the boundary of the integration from v naught to v. And the third equation is integrate this one. So it will be half v squared minus v naught squared will be equal to the integration from s naught to s a. Yes, and this makes sense, because if I integrated this part, I have v, this is going to be v squared over 2, and when you substitute with the boundary of the equation, so it's going to be v squared minus v naught squared, and this is the integration of the left-hand side. So this is if it's a variable acceleration. If it's a constant acceleration, it's the same equation, but this is going to be constant, and it's going to get out of the integral, so constant acceleration. So constant acceleration is going to be s minus s naught equal to v naught t minus t naught plus half a naught, which is the constant acceleration multiplied by t minus t naught all over squared. Last time I wrote t squared minus t naught squared. It should be t minus t naught all squared. V minus t naught is going to be a naught multiplied by t minus t naught, and the last one is going to be half v squared minus v naught squared equal to a naught s minus s naught. So basically, like for example, this equation is the same, but I got the a outside and I named it a naught because it's constant, and s minus s naught, which is the integration of the ds. So let's solve an example and see a direct application 1. So we have a car on the road. Let me make this body as the car. Let's assume that this is a car, and this card says this car on this figure moves in a straight line such that for a short time its velocity is defined by v is equal to 3t squared plus 2t, and the units are feet per second. Okay, so the velocity is function in time. Is this a constant acceleration or variable acceleration? Why? Okay, because the velocity is function in t, and when I differentiate it, so it's gonna be 3t plus 2, so it's still variable with time. But if this is first degree, like just like let's say the velocity is equal to 3t, and you differentiate is gonna be 3, so the acceleration is constant. So it's gonna be constant acceleration. Okay, so this is the velocity equation. So where t is time in seconds, determine its position and acceleration, so that's what we want to know. Determine its position and acceleration when t equals 3 seconds. Given that at t equals 0, s was equal 0, that means that the body started at rest. Like here, the body started at t equals 0, where the t equals 0, s were equal to 0. So this is s naught, because it's at time t equals 0. So let's solve this problem. Alright? First thing that you need to make sure that the body didn't change the direction. Like it's always going in positive direction. And that's actually true, because I have here a plus sign, and as the time increases, at time equals 0, the velocity is equal 0. So at time equals 0, the distance were equal to 0, and the velocity were equal to 0. Okay. But if this is minus, so there might be like changing in the direction of the velocity. And we're gonna solve an example related to this. But let's first find the position. So to solve this problem, it asks you that for the position and the acceleration at a specific time. So I need to find the general equation of the position and the general equation of the acceleration, and then substitute at t equal to 3 seconds to solve this problem. Okay, so let's look at the equations over there. This is a variable acceleration problem. Something like this. So I'm gonna use this equation to find the position s, and I use this equation to find the acceleration. No, actually the acceleration I just do direct differentiation like this one. Okay, so let's do the first one. V, I want from V to get the position, so I'm gonna do integration. So I'm gonna look at the integration over there. It's gonna be S minus S node is gonna be the integration of V dt from time t node to t. So that's what I'm looking for, S, and I know that S node at time 0 is equal to 0. So this is gonna be equal to 0. So S is gonna be equal to the integration from 0 to t of V, which is this 3t squared plus 2t dt. So when I integrate, this is gonna be
You're using that equation to find the position?
yeah, so this is the velocity,
Okay.
and I want to find the position. So you need to integrate the velocity to get the position. So that's what we were talking about. So I have the velocity, and you want to get the position, so I integrate. If I have the velocity and want to get the acceleration, you differentiate. So okay, so the first term is going to be t cubed plus t squared, and this is the general equation, okay? So if you want to find s at time t equals 3 seconds, you're gonna substitute 3 to the power 3 plus 3 to the power 2. So it's gonna be here 27 plus 9 is gonna be 36 foot. Alright, so we got the position, the general equation of the position, and the position exactly at 3 seconds. Okay, so this is the first thing. The acceleration, A, is the time rate of the change of the velocity. So you you need to differentiate this with respect to t, so it's gonna be 6t plus 2. And the acceleration at time t equals 3 seconds is gonna be 6 multiplied by 3 et plus 2 is gonna be 20 feet per second squared. The unit is very, very important. So if I give it feet, it's gonna be feet. Meter is gonna be meter. Does anybody have any question? Okay, let's solve another problem. The second problem is a car as well. Not a car, it's a particle. Like we have, this is the origin, O, and you have a particle here, is moving. And a particle moves along a horizontal path with a velocity, this equation. The velocity is described by 3t squared minus 6t, where t is the time in second. If it's initially located at the origin, determine the distance traveled in 3.5 seconds. So the time that we are looking for at 3.5 seconds. So determine the distance traveled, number one, distance traveled. Number two, the particle average velocity. We talked about the average velocity last time, and the average is v. By the way, all these problems are in Kepler, so if you want to check the reading, you go to Kepler and check it. Okay, so this is the problem. It says we have a particle. It started from an origin, and the velocity is described by this equation, 3t squared minus 6t. Keep attention to minus 6, okay? And at time 3.5 seconds, the answer for three things: the distance traveled, the average velocity, and the average speed. So let's figure this out. So since there's a distance here, so I need to find the position of this particle. How can I find the position? I integrate or I differentiate? You have the velocity. Where is it? So if you have the velocity and you want to get s, you need to integrate it. If you want to get acceleration, you need to differentiate. Okay, so let's integrate this. So you have the velocity. So I'm gonna use this equation. This one, s minus s node, equal to the integration of v dt from t node to t. Alright, so I have it start from, says, horizontal path, start from the origin. So s node is equal to 0, and you have s is the integration from 0 to t, and the velocity is 3t squared minus 6t, so it's 3t squared minus 6t dt. So when you integrate this, it's going to be 3t squared is going to be t cubed minus 3t squared. All right. And when you substitute from 0 to t, so it's going to be same one. Okay, but if you have this as 1 or 2, it's going to be different. Okay, so I got s as a function of the time. And to know that you are doing your problem right, the s needs to be 1 times higher degree than the velocity. So the velocity is a square, so there should be a cube here. The acceleration should be less degree, so it's going to be linear. So you have, the acceleration is going to be linear, the velocity is going to be quadratic, and this s is going to be from the third degree. All right, so okay, let's get the distance traveled. For the distance traveled, this is a tricky one. Because you need to figure out, is this particle a change in the direction or not? So we need to track it. Okay, since I found here there's a negative, so that means there's a possibility that this particle, it changes the direction. Okay, let's see. At time 0, t0, velocity is equal to 0, right? At time 1 second, so this is going to be 3, minus 6 is going to be negative 3. So that means it's going negative. So let's substitute with t is equal to 3. So here is going to be 3 multiplied by 9, 27, minus 6 multiplied by 3 is going to be 18, so it's going to be positive. So that means the velocity is a changing direction. So how can I know that? Or how can I know that a particle, when it changes its velocity, at which distance and at which time? So to know that, you need to find the velocity at 0. When did the particle was moving negative and then stop and making, because if you are moving a car, to go from the negative to positive, you need to stop your car. Okay? So we need to make v is equal to 0. So at v equal to 0, 3t squared minus 6t is equal to 0. So if you want to solve this, you're going to divide by t, and you will end up with 3t minus 6 is equal to 0. So t is going to be 6 over 3, it's going to be 2 seconds. So at 2 seconds, this particle changes the velocity. Okay, so the particle was moving negative, like started here, and came here, and at t equal 2 seconds, it had changed the location and came back down here. So if you want the distance traveled, you need to account for this and all this path. So you need to track it step by step. So at time equals 0, so s at t equals 0. So I have here is the equation. At t equals 0, s is going to be equal to 0. At s at t equals 2 seconds. So let's find out at what position did the particle change the velocity direction. So at 2 seconds, where the velocity is equal to 0, so it's going to be 2 to the power 3 minus 3 multiplied by 2 to the power 2. So you have 9 minus 12. It's going to be negative 4. I believe the unit of this problem is meter. Sorry, forget to put the unit, meter per second. So, negative, sorry, this is going to be 8. So 8 minus 12 is going to be negative 4. Alright, so we have negative 4 meters. So the body moved it from 0 and then make a 4 and then another 4 and then cut another distance this way. So let's find, because here I'm asking about at t equal 3.5 seconds here, which I don't know what is the distance from the origin. By the way, when we substitute at any time, this distance is measured from the origin, 0. It's not measured from here. So when I got negative 4, this negative 4 is measured from the origin. And when I try s at t equals 3.5 seconds, so it's going to be 3.5 to the power cube minus 3. 3.5 square, when you substitute, is going to be 6.125 meters. So this 6.125 is from the origin to here. So this is 6.125. So if you wanted the distance to travel as total, that this particle did in 3.5 seconds, it's going to be what?
14.125.
Like 4 plus another 4 plus 6.125. This 4 and this 4 and this 6.125. So it's going to be 14.125 meters. Does anybody have any question?
The ST is for
The total travel distance. Okay. The second thing, the average velocity. What is the average velocity? What is the difference between the average velocity and the average speed? The average speed is the total travel distance over the total time. Like this particle did 6.125, 14.125 over a total time of 3.5 seconds. So this is the total travel distance. But the average velocity, I don't care if the body goes in the negative and the positive direction. I only care about the total cut distance, just the absolute distance. You have a negative 4 and a positive 4, say, slash each other, and you end up with just a 6.125. Let's say, for example, I moved it from here to this door, so my total travel distance is 5 meters, okay? So I do 5 over the 2 seconds. But if I go 5 and I came back to my same position 0, my average velocity is 0 because I didn't cut any distance. I came to the same place, right? So this is number 1. Number 2, the average velocity V average, as we know, it's delta S over delta T, and delta S means S minus S node over delta T. So the S here from the origin, the final, is 6.125 minus 0 over 3.5 seconds, so it's going to be 1.75 meter per second. And number 3, the average speed V speed average is gonna be S total over delta T, and we just got S total is 14.125 over 3.5 seconds. So this is gonna be 4.035 meter per second. Does anybody have any question?
So you said that for the average velocity, that if you were to start at the original and then you were to go to like certain distance to come back to 0.
Yeah, because the final distance that you did is at the origin.
Okay.
So it's all about the origin position that you start from and the final position. So if my origin position is the final position, so my velocity is 0. But my speed is different because I went 5 meters and I came back 5 meters, I cut 10 meters. 10 meters over 5 seconds, so it's gonna be 2 meters per second. But if you're talking velocity, it's all about your initial position and your final position. If they both are the same, so your velocity is 0. This one. S minus S node. The final position and the initial position.
Can we do one more with asking for displacement?
We will have lots of stuff, small salt moves. Alright, so the next part that we are going to talk about is called the erratic motion. So the erratic motion is when the particle has erratic or changing motion. So the position, the velocity, and the acceleration cannot be described with one single formulation. So you need 2 formulation or 3 formulation or a graph to describe the motion. Like for example, erratic. So for example, if I gave you this and I told you that the velocity was, for example, or the distance was a second-degree parabola and then linearly. So the particle has the distance second degree in time, like t squared or something, and then it starts moving linearly. Okay, so this is what's called erratic motion. Okay, so let's solve it. It's the same thing, but the thing is, rather than solving your problem at one stage, you need to divide your problem in 2 stages. First, from 0 to t, where you have a specific formulation, and then another one here. So you need to divide you are gonna solve 2 problems, here and there. And in this one, the limit of the integration is from 0 to t, but the second problem is from t1 to t. So this is not gonna start from t. Sorry, not gonna start from 0. It's gonna start from this time. Like if this is 10 seconds, so when you do the limit of the integration, you're gonna say the integration from 10 to the time t. Okay, so let's solve problem here. So let's solve this one. bicycle is moving on a linear path, so you have a bicycle. I'm gonna represent the bicycle with a particle. Okay, so for example, the bicycles, the cars, like it's all of them are particle, like when we look at the general motion of the body. But if you look at the body itself, how the wheel is moving or how everything's moving, so it's not gonna be a body, it's gonna be something else. But we are looking at the how's the car as an overall is moving, all the parts. Same thing with the bicycle. Let's imagine that this is a bicycle, and it says that a bicycle moves along a straight road such that the position is described by the graph shown. So this graph is like this. So here, it's given in the problem, the relationship between the time and the position, and it's something like this. A curve, varies degree, until time 10 seconds, and then a line until 30 seconds, right? So this distance was 100 foot, and here the distance was 500 foot. And the equation of this curve was s equal to t squared, and the equation of this line is s equal 20t minus 100. So we have two equations. So solving these problems, but let's write the requirements first. So for the requirements, it asks you plot the relationship between the velocity and time, and the second one, plot the relationship between the acceleration and time. Okay, so since I give you the position, to get the velocity, what should I do? Integration or differentiation? Differentiation, and acceleration is differentiation as well. But I have two parts. To do them, you need to divide your problem into two parts. The first one for t from 0 to 10 seconds. And the second part for t from 10 seconds to 30 seconds. Let's do them one by one. And actually that's a very easy problem. So first you're gonna start with s equal t squared. So v is equal to ds dt. So it's gonna be 2t. And the acceleration is dd dt. So it's gonna be 2, constant. So let's get to the second part. S is equal to 20t minus 100. So the velocity is going to be ds dt, which will be 20. And the acceleration, dt is going to be 0. Because the differentiation on 20 is going to be 0. All right, I got the velocity, I got the acceleration from 0 to 10 and 10 to 30. All right? Okay, so the second thing is I want to plot the relationship. Time t, and then v, same thing, t, and a. All right, so I have this. Let's plot the velocity first. So from 0 to 10 and 30. Okay, so at time 0, the velocity is equal to 0. But at time 10 seconds, the velocity is going to be 20, right? And it's going to be linear. So it increased linearly, something like this. So this is 20. All right, and from time 10 to 30, so this is the velocity. It's going to be constant. So it's going to be constant 20 until you get to the 3. So this is actually the relationship between the velocity and the time. So I use this part from 0 to 10, and I use this part from 10 to 3. I'm going to do the same thing with the acceleration. The acceleration from 0 to 10 is constant. And it's equal to 2. So it's going to be 2, and then it's going to be equal to 0. Otherwise, So all this is 0, but you have acceleration from 0 to 10 seconds, and it's equal to 2. So this is the relationship between the velocity in time and the acceleration in time. Does anybody have any question?
You need 30 here, right? Like 30 seconds?
Yeah, 60 seconds. 0. If you have any question at any time, just ask me, stop me and ask if you don't follow something that I wrote on the board. Okay. So let's make this more definite, like the rapid motion. So right now, I give you S as a function in time, and I ask you for V and A. But what if I give you A, and I ask you about the other things, the velocity and the acceleration? As you see what we did here, we integrated S, we differentiated S to get velocity differentiation is much easier. So to get the velocity and another differentiation to get the acceleration. But I give you the acceleration, you need to do integration to get the velocity and another integration to get the position. Okay, so for this problem, the next one says that you have a car starts from rest and travels along a straight track such that the acceleration is described by this curve. So you have a car, start at rest, and this is the time, and this is the acceleration. And the acceleration was constant and positive, equal to 10 meter per second squared. And at some point, t equal 10 seconds, the body starts to decelerate until uncertain time that we don't know t dash. Okay, so the body was accelerating with 10 meter per second squared, and then at time t second it started decelerating, like it was speeding, and then it started to slow down until it came to velocity equal to 0 and acceleration equal to 0, and the deceleration rate was negative 2 meter per second squared. So this is A1, and this is A2. And we are talking about a car, like we have a car, it's moving, and we can describe the movement with this acceleration. Alright, so what is the requirement? The requirement draw the relationship between the velocity and time, and draw the relationship between the position and the time, and determine the time t dash needed to stop the car. Like at the time t dash, like the car is slowing down, how much time with this deceleration rate this car is gonna stop. Alright, so let's start this problem. We have the acceleration. So as we said, if we have the acceleration and we want to get the velocity, we need to integrate. But this is an erratic motion, not constant motion. You need to divide your motion. So first thing that I'm gonna do, 1 for t more than 0 and less than 10 seconds. I have the acceleration is constant and it's positive 10 meter per second squared. So what I'm gonna do, if you wanna go back, you can go back to the rules. If you wanna do it very quick, maybe you can write that A is equal to dv dt. So dv is equal to A dt, and then you can integrate both. So you'll have v minus v naught. Is going to be the integration of this one from t naught to t a dt. Alright, so I have v naught is equal to 0. Why? Because in this problem it says that the particle starts from rest. Starts from rest, that means at time equals 0, s were equal to 0 and the velocity was equal to 0. So v naught was 0 and t naught was 0. So v is going to be equal, so I can slash this, it's going to be 0. The integration from 0 to t of 10 dt, so it's going to be 10t, alright? So I did the reverse integration. So if you want to get s, as you know that v is ds dt, same thing. So if you want to get ds is going to be the integration of v dt from t node to t, and here from s node to s, so s minus s node is going to be the integration of v dt. By the way, if you want to know the velocity, and you know that the velocity is the integration of a dt, so it's the area under this curve. So at time 10 seconds, the velocity, if you get this area, like here the velocity, is the integration of a dt. So if you get this area, 10 by 10, 100, so the velocity is 100. Or you can substitute here right away. V at t equal 10 is going to be 10 multiplied by 10. It's going to be 100 meters per second. So either you get the area under the curve or you substitute in the equation. All right, so we got the velocity. Let's get the distance here. S minus S naught is the integration. I have S naught is 0, so S is going to be the integration from 0 to t, which is 10 seconds, and I have V is 10t dt, so V I have it here. So what is this is going to be? The general rule of S is the integration of 10t is going to be 5t squared, right? When you integrate t, it's going to be t squared over 2. It's going to be 5t squared. This is the general rule, but if you want to put the integration limits from 0 to 10, so it's going to be 5 multiplied by 10 squared, so it's going to be 500 meters. Okay? Does anybody have any problem with that? Okay, so what I did, I have the acceleration, I integrate once to get the velocity, I integrate another one to get the acceleration. The position. Very simple. The integration of 10 is going to be 10t, the integration of 10t is going to be 5t squared. Very simple. If you want to substitute at 10 seconds, so 10 multiplied by 10 is going to be 100, and S5 multiplied by 10 squared is going to be 500. Very simple. Okay, we are done with the first part. So let's get to the second part, where we need to be more focused on the second part. For t more than 10 and less than t dash, the time that we don't know. Does anybody have any question? All right. First, I want to find out what is the t dash, but to find the t dash, I can put the velocity equal to 0, but I still don't know the velocity here. So first, I need to find what is the value of the what is the equation of the velocity here, and then I put the velocity equal to 0, and then get the t dash. So let's do this. All right, I know the acceleration. The acceleration a is equal to -2. So if you want to get right away the velocity, I know it's gonna be. But right now, if you did the same thing like what we did here, 10t, and then from 10t, 5t squared is going to be wrong, because the boundary of the integration is different. Here it starts from 0 to 10, but here it starts from 10 to t dash. So what you are going to do, you are going to follow the rules step by step. Like you are going to say that v minus v naught, the one that you have it in the sheet here. But let's just start, this one, v minus, here, v minus v naught is the integration, t naught, t, a, dt. All right, v naught right now is not 0, it's the velocity at 10 seconds, and the velocity at 10 seconds, we just got it, it's 100. So this is not 0, v minus 100, because my naught is not 0, it's t 10 seconds. And here is the integration from 10 seconds to t, and this is gonna be a, which is -2, dt. So this is going to be v minus 100, and this is going to be -2t from 10 to time t, so it's gonna be negative 2t minus, it's gonna be positive, plus 20. Right?
T squared.
So we are integrating negative 2. So it's gonna be negative 2t.
For the upper limit of it. If you're on
But you are gonna replace t with t dash, so you can't put t dash of something. Right, so right now we can leave it t or t dash, whatever. It's gonna like I named this t dash, but if you put it t, that's fine. Okay, just like a symbol. Right now we have v minus 100 equal negative 2t plus 20, so you can write this as v equal to negative 2t plus 120. So I got the relationship between the velocity and time for this interval. The second part is that we need to get the position. So the position, s minus s naught, is the integration from t naught t dt. Right, s naught is not 0, because s naught is the s at 10 seconds, which we just got here, is equal to 500. So s minus 500, the integration from 10 seconds to t, and the velocity equation is 2t plus 120, negative 2, sorry. So this is gonna be negative t squared plus 120t, and you are gonna substitute from 10 to t, or t dash, whatever you're gonna put. So this is gonna give you, once you put 10, once you put t, so it's gonna be negative t squared, let's put that, minus 500, so it's gonna be negative t squared plus 120t, and then you substitute with 10, so you're gonna put minus, and you're gonna open a parentheses, and then you're gonna have a minus 100 plus 1200, so this is gonna give you, and once you solve this, you're gonna find this as equal to 120t minus t squared minus 600. Alright, so I did everything, but I still didn't plot VT and ST, but I have what it takes to do this. So what it takes to do this, I have the equations. So let's plot them. First, I'm gonna plot the velocity. And then I'm gonna plot the position. Alright, so let's do them step by step. The first one is the velocity from 0 to 10, and I have this equation, 10t. At time equals 0, the velocity is equal 0, and at time equal 10, the velocity is 100, and it's linear relationship. It's 0 until it gets to 100. Alright, so from 10 to t dash. From 10 to t dash, we have v is equal negative 2t plus 120. If we want to make sure that we solved the problem correctly, if you substitute in both equations at 10 seconds, it should give you the same number. So if you put 10 here, multiplied by 2, it's going to be negative 20, plus 120 is going to give you 100, the value that we have here. The thing is, I don't know what is the time here to continue the line. So I have 10 seconds, but I don't know what is the time here, and it says the time here is where the particle stops, so which means where the velocity is equal 0. Okay, I have two equations of the velocities. Which one should I use? Should I use this one, or should I use this one? The first or the second? The second. Why? Because this time is in the second interval. So I'm gonna put velocity negative 2t plus 120. So if we put this equal to 0, so we're going to end up with t is equal 120 over 2 is going to be 60 seconds. So this is going to be 60 seconds. All right, the velocity at 60 seconds is equal to 0. So I'm going to put this something like this. So I got the time where the body stops. And second thing we're going to do is that we plot the time versus the position. Let's get to the first equation. 5t squared, it is a quadratic equation, so basically it's going to be something like this. At 0 it's going to be 0. At 10, 5t squared, so it's going to be 500 until this point. So the second equation, this one, it's another quadratic equation but has different things. If you want to plot this, you are going to pick 3 points. So we have up to 60. So you substitute in this equation with, for example, 20, 40, and 60, or 20, 30, 40, whatever number. The more points you are going to create, the more accurate shape. So it's going to end up with like a curve something like this. To do it, you substitute at t equal 20, 30, 40, 50, until you get to 60. And then you get the second curve. So we plot both the relationship between the velocity and time. Does anybody have any question on this?
Why would it be starting at
With negative
negative 600?
600 here?
Yeah, like at the beginning, right? Because if it's when t is equal to 0, you have a if you're using out, right?
No. Okay, so we have the motion on 2 parts, right? This is the first part from 0 to 10 and from 10 to 60. You cannot mix the equation. From 0 to 10, you need to use this equation. Where is it? This one.
Oh, okay.
But in the second part, you should use this one. That's why I'm saying you need to focus, right? So that's why you need to focus on what equation that you should use when you substitute with numbers. So when I plot this curve, I start from here and I substitute with this number in this equation. Okay, so right now we are going to talk in the next 20 minutes in the next topic. Does anybody have any question to close the rectilinear motion?
I got a question. So,
I can't hear you.
at 10, it's supposed to be 500 or 50 on the bottom one?
This
On
one?
the position one.
This is 500.
Okay.
So 500, why? So at this point, you can substitute in the 2 equations at 10 seconds. So if you substitute at 10, so this is going to be 1200 minus 100 minus 600 is going to be 500. If you substitute with 10, and 5t squared is going to be 500 at the point of the intersection between the 2 curves.
What is the S equation of the last number? Like t squared minus.
This one? 600. Okay, so the next topic is the curvilinear motion, which is a little bit difficult from the rectilinear motion. So chapter 12.4, curvilinear. So the curvilinear motion occurs when a particle moves on a curved path. Okay, so curved path, something, let's say for example, something like this. And you have, like you are driving your car and you're driving your car on a curve. So this is a curved path. So this is something, your car is here, and this is the origin of the curve, or the center of the curve. We describe the position of this car by a vector, like this vector. The position vector R, something like this. And if the car moving this fast came here, so
So this is the new position vector, r dash. If you guys remember from vectors, the vectors is something like this. So I'm saying that this is r. A vector, it has two components, right? X direction and y direction. So you have an x component like this and a y component like this. So if you are analyzing this vector, you are going to say this vector has a component rx and component ry. So for this point to move from here to here, so it can make this movement as rx in the I direction. Do you guys remember the I direction and y direction, the unit vectors? So it needs to cut a distance of magnitude rx in the direction of x-axis. This is the unit direction. And magnitude ry in the direction of y-axis, which is j. So this is the unit vector I, and this is the... Does any of you don't know the vectors, quantities? Okay, so this is how we describe the motion with r vector. So the r vector has two components. The first component is the magnitude and direction. This is the position. All right, so what I care about is the change in the position line. This absolute distance between the two positions, like from here to here. And we call this delta r, okay? However, this particle, when it moves, like your car, when it moves along this path. It didn't move to this path. But when we talk about position-wise, it doesn't matter what path that this car did. Like, let's say that this car moved this way, all this way until it comes here. It doesn't matter. What matters, the change in the position. Do you guys remember my example? If I'm here and I went to the door and I came back to my origin, so I didn't cut any distance, and my average velocity is 0. But the same thing for a curved path. It doesn't matter what is path that you take. What matters is the absolute location, like the change in the position with respect to the origin. Okay? All right. So in our example, the car run on this position and cut a distance S total is this curve. Okay, so let's find the same things that we did before for rectilinear paths. So let's talk about position, number 1. Position. So the position is the change in the particle position. That's what we talk about from here to here, which is delta R, which is the final position, this R vector, minus the initial position. So this is the change in the position. And we call this displacement. What is the displacement of this car? So it displaces it from this position to this position. The next thing is the travel distance, or the distance traveled. Distance traveled. The distance traveled is the S total, which is all this curved path. Okay, does anybody have any question on that? All right, so this is for the position. The second thing is the velocity. So for the velocity, I have 4 components. So number 1 is the average velocity. Number 2 is the instantaneous velocity. Number 3 is the average speed. Number 4 is the instantaneous speed. Alright, let's talk about the instantaneous velocity first. The instantaneous velocity is the rate of a change in the position. Okay, so if you want to write, and actually that what we call it the velocity vector. V something like this is the change of the position. So if you have this position R, so we write it as dr dt. Okay, and dr as a vector, not as a scalar, because the velocity can change in the quantity, like the magnitude and the direction. Like if you have this curved path and your particle is here, the velocity is always tangential to the path, like something like this. So this is the velocity 1, and when the particle is here, the velocity is here. Sometimes the velocity can keep the magnitude as the same, but it changed the direction. It's going this way, but here v bar is going in a different direction, okay? And the velocity is always tangent to the path, always, okay? So here's the particle, and here is the particle. So the velocity is the time rate of the change of the position of the particle, and we can write it as r dot. So both are the same. The second thing is the average velocity. Let's get here, v average. V average is the delta r, this one, this thing. I don't care about the path that the particle did, I only care about the change in the position. The final position and the original position. You subtract them, so delta r vector over delta t. So this one gives you the velocity at any time, here, 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 here. So it's gonna be function in time, and you can substitute with the initial location and the final location, delta r, so r dash minus r over delta t. So once you have the instantaneous velocity, you can substitute at the final with the time at the final, and then you get the final position and the last position, and you divide them by t, okay? The average speed, so the average speed is the same thing, it's the delta s or the s total, like we can say this s total or delta s. So let's keep it delta s so that we can be consistent with the nodes. So it's gonna be v speed average. So as we said, speed is that we are here about the cut distance. So if this is gonna be a different path, so I'm gonna only focus on the s total that the body did. So it's gonna be delta s over delta t. I'm curious about how much distance that you cut to get to the next point. And then I divide it by the total time that I have to cut this distance. Instantaneous speed is like, you think about like as this as a linear path, not as a curved path. And then you differentiate d delta s, ds et. Like if I told you this car is moving on this path, and I give you that the rate of change, like s, is it changing over time? S is equal to 2t squared plus 2. But this is the distance that you are cutting on this linear path. You differentiate it with respect to the time, you will get the instantaneous speed. Okay? But if I'm asking about the instantaneous velocity, so we are curious about the change of the position, r. Okay? So there's difference between r and s. S is a distance, r is a position. Okay? Alright, does anybody have any problems so far? Alright. So the second thing that we need to talk about is the acceleration. So when you go home, try to put this in front of you and keep differentiating. What's the difference between speed and velocity? What's the difference between position and distance? And try to distinguish between these two things so that you can make sure when I ask you in a problem what is the instantaneous velocity is and what is the instantaneous speed is. So they are completely different two quantities. Same thing with the acceleration. So if we're talking about acceleration, we're done with the position, velocity. Number 3 is acceleration. We have two quantities of the acceleration. The first one is average acceleration and instantaneous acceleration. Okay, let's start with the instantaneous acceleration. The instantaneous acceleration was the A vector, which is the time rate of change of the instantaneous velocity. So dv dt. Okay, so you have the velocity here is v and keep it changing. So we have how v is changing over time. And then if we differentiate it, you are gonna get the instantaneous velocity. Same thing, you have the r vector, the position. You differentiate r, you get v. You differentiate v, you get a. But right now it's the vectors because it's on a curve. We can write this as v dot, or we can write it as r double dot. Why? Because I know that v vector is dr dt, which is r dot. So we differentiate r one time with respect to the time, you are gonna get v. Another time you are gonna get a.
I'm sorry, is it possible to put the monitors down? Like,
To put what?
the monitors here, can you put these down?
No, the monitor.
The monitor,
Oh,
the
the
computer
computers?
screen?
Down, like down where?
Like out of the
Oh,
way.
Thank you very much.
Can you try to put it on the other side of the desk?
Oh, yeah,
No,
that
no,
sounds
no.
better.
Yeah. Can you do the other one as well?
So I'm gonna look from here.
Yes.
Can you do the other one as well, sir? Thank you very much.
Yeah, oh, that one.
Okay.
Perfect.
So. Alright. So right now I have the instantaneous acceleration. As I said, if you want to get it, you can differentiate the velocity one time with respect to the time, or you can differentiate the position two times. Okay? The average acceleration, I don't care about the instantaneous, I want the final and the initial. So the average acceleration, A average, is gonna be equal to delta V dt. And this
Oh, there's more.
is the vector, and this is gonna be the V, the final V minus the initial V over delta T. Right? Does anybody have any problem? Okay. So instantaneous position, instantaneous velocity, and instantaneous acceleration give you the acceleration at any time. But if you want to get average, you want to know initial and final. Once you know the initial and final, how can I get it? I substituted the instantaneous with time 0 and the final t. You get two quantities, subtract them, divide them by t, you get average. And the only thing that you need to take care about, if I'm asking about velocity and speed. So it's completely different quantities. Velocity, so I'm only care about the final position. Speed, I'm curious about the path that you take to get to this position. So to do curved passes, there's different ways to do them. So we need to be familiar with the coordinate systems. So coordinates is the last thing. Alright, so we can deal with three different types of coordinate systems. Number one is the Cartesian coordinate system, which is x and y. Or number two, this is my opinion to you, it's a tangent normal. And we say t and n. And number three is a polar coordinate system, which can be r and theta. So if you have a particle that moves on a path, so you either use a Cartesian coordinate system, like you are saying that this is the origin, and you have x and y, and this is Rx, and this is Ry. Okay, so this is Cartesian coordinate system. But if you want to do, you can do also what is called tangent and normal, like you make tangent and normal direction, and you work with the tangent and normal direction that you have here. Or you have a polar coordinate system, which you call this R, and then you have theta. So when you define the position of this point, you say, for example, 5 and 10. This is Rx and Ry. Or somehow you put what is the tangent and normal. Okay? Or somehow you say that R, for example, is 100 and theta is 3 radians. Okay? So this is how we describe the position of a particle using these coordinate systems. But when I give you a problem, I'm not going to tell you what coordinate system that you are going to use. You need to figure it out by yourself. What is the best coordinate system that I need to use in my problem to make my problem much easier? So, for example, if my particle is if we are talking about gravitational acceleration, like the body is moving linearly, so we are going to use like Cartesian coordinate system, or like the body's like falling with the gravitational, or is moving with linear acceleration. So x and y is perfect, like we are saying here, gravitational acceleration. If the body is moving on a path, like a path that is not circle, like a path that has a curve, and I'm telling you where's the center of this curve. So tangent and normal is perfect. We're going to solve examples of this. If the particle is like you have an arm is rotating on a fixed location, like you have an arm, and this arm is here, and your particle is here, and this arm is moving in a circle, so r and theta is perfect. Arm is moving around the fixed location. Okay, so these are the two coordinate systems that we are going to use for curvilinear motion. Curvilinear motion is a little bit difficult from rectilinear motion. Next time we're going to solve some examples and see how we can work out with, we are going to do the same thing, but rather than linear motion, we're going to have curvilinear motion. See you guys next time. The homework is due next week. You have 2 problems. I upload the notes like after the lecture, so you can check the notes. And also you can check the textbook for the exam. Yeah, it's gonna be file upload on campus. So you write them, take them and upload your phone.
I think this is what I expected. Physics 2.
Yeah, should.
And then it This has nothing to do with physics 2 though. I don't know why we have to.